Okay, this is a logistic differential equation. What you should be thinking is, if you recall, this is your general form for a logistic differential equation. These are those graphs that start out exponentially and then level off, so it looks something like this. Okay, part A, they're telling you that the initial population of whatever they're talking about here is 3. So let's say we're talking about bears. There's 3 bears. What happens to the population as t goes to infinity? Okay, there's no work to be done here. This is, do you understand the characteristics of a logistic differential equation? Remember, this number here is called your limiting capacity, so this is what happens as the limit as t goes to infinity. So if you know that, right away you can come up with that first answer is 12. Now you want to make sure when you're working with these logistic differential equations, it's exactly in this form. Sometimes this may not be 1, it's a different value, and you may need to factor it out. Okay, they ask you another question in part A. What if the initial population of these bears was 20? What happens as limit time goes to infinity? It doesn't matter what the initial population is, all of these graphs approach that limiting capacity. So you should list 2 answers for part A, both of them are 12. Part B, if P is equal to 0, if P of 0 is 3, so you start with 3 bears, for what value of P is the population growing the fastest? If you remember, another characteristic of a logistic differential equation is the steepest slope, which is where the population grows the fastest, always occurs at the point of inflection, which is always at half the limiting capacity value. So L is 12, so I know it always happens when P is 6. That's it, you're done. No work required. Okay. Part C. They give you this differential equation and find y of t. The thing you want to notice here is this is not a logistic. Notice it says a differential equation is given. They don't tell you it's logistic. It may be, but notice it does not fit this model because I have ky here, 1 minus. This is a different variable. It's not the same as this y, which is what it needs to be. So they're asking you to solve this. So this we are going to go ahead and solve by separating our variables. This is your, okay, step 1, get your variables together. Let's separate them. So I'm going to move this y over here. Everything else I'm going to go ahead and leave on the right side. So I end up with this. It's up to you what you want to do with this 5. Some people will move it here. I'm just going to leave it on this side. So I'm going to take the antiderivative of both sides, integrate it. This is natural log of y. I'm going to go ahead and multiply this out. So the first term is 1/5. Antiderivative is 1/5 t. This becomes t over 60. So I get t squared over 2 times 60, which is 120 over plus c. Okay. If you remember, we have to solve this for y. So I'm going to rewrite it as an exponential. So y is equal to e to the 1/5 t. All of this becomes your exponent. And if you remember, we talked about this can be broken up, e to the 1/5 t, e to this, e to the c, but e to the c is really another constant, multiple. So I'm going to rewrite the problem like this. Okay, and you can go straight from here to here. You don't need to show this algebraic step. Okay, now they give you a point. They tell you that y of 0 is equal to 3. So if I plug in 0 for t and plug in 3 for y, you should get a c value of 3. So here's my equation. So here's my solution. Part D, now they want you to find the limit of this function. So let's find the limit as t goes to infinity of 3e to the 1/5 t minus t squared over 120. Okay, this is a non-calculator problem. So what you want to think about doing is, what do we do when we have negative exponents? We always simplify it. So I would rewrite it like this, right? This is a negative exponent piece, so I'm going to go ahead and drop this to the bottom. Okay. If I plug in infinity, this piece becomes infinity. Anything divided by infinity is 0. And there's no work to be shown here. You can go straight to that 0 value.